So, thank you for, so first of all, I'd like to thank the organizers for giving me a chance to talk about our recent study about the finite temperature excitation spectrum of the spin-orbit coupled multi-issues. First, let me introduce my motivation, why I'm interested in the finite temperature excitation spectrum in the spin-orbit coupled multi-issues. And later, I will be discussing about frustration in the spin-orbit multi-issues. And I'd like to give you some introduction for some materials, sodium iridate oxide. It's a really typical example of the spin-orbit coupled multi-issues. And then later, I will switch to the finite temperature spin dynamics, and I will introduce a new algorithm to calculate the finite temperature spin dynamics, and I will talk about applications of this algorithm to the proximity of the quantum spin liquid phase. And I'd like to summarize and discuss about our achievement. Okay, let me start with my motivation. The first, I'd like to identify the quantum spin liquid behavior at the finite temperature. This is my motivation. Because usually, if we try to find the quantum spin liquid, how to characterize the quantum spin liquid is naively the alibi of the spontaneous symmetry breakings. If you're cooling down your multi-insulator or spin system down to the absolute zero temperature, and if you don't have any spontaneous symmetry breaking, then you can have a quantum spin liquid. But it's a kind of the negative proof, or kind of the proof we cannot prove. So I'd like to capture some finite temperature signature of the quantum spin liquid. Here I will show you some example of the quantum spin liquid phase diagram. The vertical axis is the log scale temperature in the log scale, and the horizontal axis is the strength of the perturbation to the exactly solvable quantum spin liquid system called as Kitaev models. Here I add the Heisenberg term to the Kitaev model, and if you apply enough large perturbation, then your system will deviate from the quantum spin liquid phase and showing the magnetically ordered phase at the absolute zero temperature. If you're raising the temperature in this system, we have two typical temperature scale here, here and here. But the problem is how to characterize this quantum spin liquid phase at the zero temperature from the finite temperature property. Because in the experiment, we only access about physical properties at the finite temperatures. This is our motivation. And to study this kind of the physics, the spin-orbit coupled multi-insulator is the best playground for us. Because first of all, the frustrated magnetism in the spin-orbit coupled multi-insulators provide us the frustration from the anisotropic exchange. It's different from the geometrical frustration in the Heisenberg model on the pyropolar lattice or Kagome lattice. And if we weakening the frustration, then we can enjoy the physics in the triangular lattice Heisenberg model physics. It's already talked by the Professor Christian Battista in this morning. And in addition to that, the frustrated magnetism in the spin-orbit coupled multi-insulators provide us a really interesting playground, because we can have some exactly solvable limit inside this physics or inside this playground, and we can enjoy the proximity to this exactly solvable limit. This is really important property of this system, and let me introduce briefly. So first of all, let me make my target concrete. Here, I'm interested in the physics in the Iridium oxides or Ruthenium halide. This category of the compound, including the Iridium 214, Iridium 213, and the Iridium 227, and this compound 213 is the compound of our interest. Here, there is competing or cooperating Coulomb repulsion and spin-orbit coupling. If you look at the T2G manifold in this oxide, and if you write down some ab initio effective Hamiltonian for the T2G manifold, then you can figure out that the interatomic Coulomb repulsion in this system is around 2.5 electron volts. It's compared with the large spin-orbit coupling. It's roughly speaking the 0.5 electron volts. And then your d orbitals in the iridium tetravalent iridium atom split it into the T2G and the EG under the cubic environment. And in addition to that, if you have spin-orbit coupling, then this T2G manifold is split it into the doublet and counted. And in the tetravalent iridium ions, we have one hole here. So in this sense, this is a spin 1/2 system. Or in this community, we call this state as a J-effective 1/2 state. And in some sense, this state is relativistic generalization of the cuprate doublet in the kappa divalent ions. And in addition to this iridium oxide, not recently, but 5 years ago, the ruthenium halide participate to the same kind of family, because if you look at the ionic state of the ruthenium ions, then the electronic structure is quite similar to these iridium ions. And if we have this kind of the ionic state on the honeycomb lattices, it's realized in the iridium 213 or alpha ruthenium halide, then we can have a really interesting physics. It's first proposed by George Jacquerie and Guinea Kalurin around 2009, and also around 2009 or around 2006, and then later their collaborator A.D. Charupka clarified much more in detail. But anyway, if you have a spin-orbit coupling and if you have a doublet on the honeycomb lattice structure, then there is some spin lattice locking. Here I show you the honeycomb lattice structure consisting of the iridium ions. And here, if you have a spin-orbit coupling, then you may have a bond-dependent interactions. And based on their prediction, this kind of Ising interaction, bond-dependent Ising interaction, become dominant in this system. And for example, this horizontal axis, the spin interaction is connected by the Z component along this axis. Spin-spin interaction is given for the Y component, and for this bond, we have XX exchange coupling. And then this kind of the physics, this kind of model called as a Kitaev model, and it's already examined in the lecture and the seminar, for example, by the Dr. Hyun Lee in the last week, if I remember correctly. So some of you already know about this. And let me explain a little bit more. First of all, if you have a spin and the lattice locking, then you can thinking about lattice rotation. For example, if you put the Cartesian axis like this, and this x-axis is perpendicular to this bond, and this y-axis is perpendicular to this bond, and this z-axis is perpendicular to this horizontal bond, then if you rotate your system around the 1, axis, then you can make exact mapping from these guys to this guy, and these guys to these guys, and vice versa, and simultaneously. So in this sense, if you have this kind of anisotropic interaction, then it's really compatible with your lattice structure. If you have a spin-orbit coupling and if you have a spin lattice locking due to this relativistic effect. And from the symmetry of the oxides or halides, usually, ideally, this iridium ions or ruthenium ions is surrounded by the oxygen atoms, and the oxygen atoms form the octahedron. And if we have an ideal octahedron, then the iridium ions are connected by the 90-degree bonding from the d orbital to the p orbital in the oxygen and the d orbitals. Then, if you utilize this symmetry, for example, here, along this bond, we have a 001 mirror symmetry and a 01 bar 0 mirror symmetry. Then the symmetry allowed interactions is given by this. In this matrix representation for the exchange coupling, the 3 independent coupling constants can appear. J is the usual Heisenberg coupling, and K is the Kitaev coupling, and gamma is so-called off-diagonal exchange coupling, or just we say call this interaction as just as a gamma coupling. And if you write down this Hamiltonian for this bond by using spin operators, look like this, and this matrix form is just representing this situation. And usually, if we only have this kind of DPD hopping, and this hopping generates a spin-spin interaction among these two ions, then we only have a dominant Kitaev coupling. But in addition to this kind of hopping, we have, in the real compounds, we have several exchange paths, and in this kind of exchange paths, we introduce this kind of coupling, and this Heisenberg coupling together with this gamma term. It's already examined by these people. Okay. Then let me examine how this system shows the frustration. The first, we assume that the Kitaev coupling is dominant, and we only take into account this Kitaev coupling here. And usually it's become negative in the Ruthenium compound or Iridium compound. So if you try to find the classical ground state of this lattice Hamiltonian, the one possible ground state is something like this. Here, the spin, all spin pointing along the z direction. This gives you the one candidate of the classical ground state. However, if you remind that only the z component of the spin are interacting through this horizontal bond, then if you flip one pair of the spins, then you can keep the energy as the same as this configuration. So in this sense, you can flip another pair of the spin and another pair of spin and spin. Then you can generate many classically degenerated spin structures. And this is really give you the macroscopic degeneracy. So only when you introduce the quantum fluctuation, this degeneracy is lifted. Unfortunately or fortunately, there is some topological degeneracy at the ground state for this Kitaev model, revealed by Alexei Kitaev himself. But anyway, the quantum fluctuation can melt this macroscopic degeneracy, and you will end up with several degenerated ground state at the zero temperature. And this frustration does not coming from the geometrical frustration, but coming from the anisotropy of the exchange couplings. It's originated from the spin-orbit coupling or relativistic effect in the heavy ion systems. Okay, so in addition to this Kitaev limit, we also have an interesting limit in this Hamiltonian. In the former slide, I just introduced in the K only, but if you only have a gamma, again we have interesting physics. It's called as a gamma limit. And in this paper, by the Ionic Rousseau, sorry, I cannot pronounce his family name, but Ionius and Natalia Parkin's paper give us the really interesting physics of the classical macroscopic degeneracy at the gamma limit. And if you look at the real compound, as I already said, usually we can have a Kitaev coupling. In addition to the Kitaev coupling, we can have a Heisenberg coupling also. This is examined by this situation examined by these papers by Georgia K. Karyurin and their collaborator Ili Charpka. And what they found is something like this. If the Heisenberg term is enough small compared with the Kitaev coupling, then we can enjoy the spin-negative physics. But we introduce further larger exchange coupling in addition to the Kitaev model, Kitaev coupling, then we will have a magnetically ordered ground state. So around 2010, there is many discussion about sodium iridate, because if you do the neutron scattering, then the people found that there is a zigzag magnetic order. Here you have a zigzag chain with the ferromagnetically ordered spins, and it's coupled with the neighboring chain in the anti-parallel fashion. However, this kind of order cannot found in the phase diagram of the Kitaev-Heisenberg model if the J is positive and the K is negative. So there is many debates, and we're also working on these topics with the ab initio Hamiltonian. And here just in case I prepared a slide to describe in the ab initio effective Hamiltonian, but I will skip this part. If you're interested, then please ask me a question. There is some way to construct the effective spin Hamiltonian starting from the DFT theory and constructing the T2G Hamiltonian. And if you take a strong coupling limit and do the second order perturbation from the second strong coupling limit, then you can derive the spin effective Hamiltonian for this system. And this is our result for the ab initio Hamiltonian, spin Hamiltonian for the sodium iridium oxide. And here there are several couplings. And actually speaking, this shaded coupling is the dominant coupling, and it's nothing but the Kitaev coupling. And actually, this coupling is dominating in this effective ab initio effective spin Hamiltonian. However, other detailed coupling give us the zigzag order. And first, we examine this situation with the exact diagonalization, but later, our collaboration with Okubo-san, maybe here, and together with Shinjo-san, we found that even in the IPEPS and the DMRG method, we can reproduce the zigzag order found in experiment. This is really old story, 2 years ago or something. And but starting with this kind of ab initio Hamiltonian, we can tackle the finite temperature signature of the Kitaev model or Kitaev spin liquid, because anyway, even if we have a zigzag order at the ground state, as a ground state, still our effective Hamiltonian is dominated by the Kitaev coupling. So maybe if we go beyond the nail temperature, and if we look at the high temperature properties of this system, then we can figure out the signature of the spin liquid phase at the ground state. And let me briefly introducing the thermal excitation, property of the thermal excitation in this system by using the thermal pure quantum state method developed by these so many authors independently. And recently, the Sugiura-san, formerly he did the research in this ISSP, found a very nice theory and algorithms independently. And afterwards, we realized that there is many independent effort about the finite temperature property of the quantum many-body system. But anyway, now we can calculate the many finite temperature property based on these theories. Anyway, let me start with the entropy or heat capacity of the system, because it's really important physical quantities in our effective Hamiltonian. First, if we can measure the entropy, then we can capture the idea of how many degrees of freedom is really important in this system. For example, if you look at this paper, then they give us the hint, because the Kitaev model is exactly solvable at the ground state, and exploit these properties. Then these people, Dr. Nasu, Professor Nasu, and Professor Udagawa and Professor Motome, found a way to calculate the finite temperature property of the Kitaev model by using the Monte Carlo. Then they can calculate the thermal excitation of the Kitaev model. And they found that the spin degrees of freedom break up into the two objects even at the finite temperature, and this is observable in the temperature dependence of the entropy. So if you calculate the temperature dependence of the entropy, then we have this kind of the behavior. And here we have some shoulder. And if you divide this curve into the two smooth function, then we can figure out that this shoulder is coming from the separation or plateau in the entropy. So that this is nothing but half plateau in the entropy. This signaling the decoupling, or sorry, the division of the spin degrees of freedom into the two objects, or 2 degrees of freedom. And this kind of separation is also found in the ab initio Hamiltonians. Here, I will show you the heat capacity data for the Kitaev limit of the sodium iridate. And this is ab initio limit of the sodium iridate. Here we have many detailed coupling together with the Kitaev component. So we just leave the Kitaev coupling in the ab initio Hamiltonian and scale down the other detailed Hamiltonian, like this. And then we can interpolate the Kitaev model and ab initio Hamiltonian for the sodium iridate by changing this scaling factor lambda. Then this is corresponding to lambda equals 0, and this is corresponding to lambda 1. In any case, we have a peak structure in the heat temperature dependence of the heat capacity. And then here the horizontal axis is temperature in the log scale, and the vertical axis is the heat capacity in the unit of the joule per mole Kelvin. And here I show the result for the 12 to the 32 spin clusters. And here for the ab initio model, we have a good convergence with the system size. And the most severe finite size effect appear in this Kitaev limit. But anyway, in any cases, we have two peak structure in the heat capacity. And if you integrating this, so anyway, you have two peak structures, sorry. And if you calculating the second derivative of the ground state energy with respect to the lambda, then we will find this kind of peak structure around the lambda around the 0.6. And this signaling the second order phase transition from the spin liquid to the zigzag order. And if you look at the square root of the structure factor, it's corresponding to the magnetization in the finite size system, or estimation from the finite size system. Then around this 0.6, we have a rise in this zigzag order. Sorry, here our magnetic structure factor has a Q momentum dependence, and I just picking up this typical momentum. And here, this blue momentum representing the zigzag order found in the experiment. And if you're tracking this curve, it's rise around this coupling constant, and it gives us the signature of the magnetic order in the thermodynamic limit. And if you calculate the heat entropy, temperature dependence of the entropy, then always we have a shoulder-like structure, starting from the Kitaev limit to the ab initio limit. In the ab initio limit, it's not so visible, but we can divide this entropy for the ab initio limit into the two parts, and we can analyze the weight of these two parts. From Kitaev limit to the ab initio limit, the weight is around 1. This means that this separation is almost weight of these two separated weight entropy has more or less the same weight. This means that starting from the Kitaev limit to the ab initio limit, there is some finite temperature fractionalization of the spin degrees of freedom, even if we have a magnetically ordered ground state for this side of the zigzag order. And if you look at the heat capacity and compare with the experiment, the agreement is good, more or less good, because this is calculated for the ab initio Hamiltonian for the sodium iridate with 32 side spin clusters. We can directly compare with the experiment without no adjustable parameters. Here, this is all the experimental result of the heat capacity. It shows a good agreement. And later, the motivated our theoretical prediction of this high temperature heat capacity. The Indian group re-examined the heat capacity, and they found a high temperature peak exactly around this temperature. And by using these two peak temperature and scale, and take a ratio of these two temperature scale and plotting as a function of the lambda, then we found another interesting physics happened in this system, because inside the quantum spin liquid phase, this ratio remains constant around the 0.03. But in the magnetically ordered phase, this rapidly rise. So in this system, if you measuring the heat capacity and take a ratio of two temperature peak, then you may find some quantitative condition to obtain the quantum spin liquid phase. It's formulated as like this. This ratio should be smaller than 0.03. However, maybe many of you already know the heat capacity measurement is really difficult, because always if you're measuring the heat capacity in the lattice system, you will have a lattice contribution in the heat capacity. And the subtraction of this heat capacity from the lattice degrees of freedom is not so easy. So in this sense, that we need much more information about the finite temperature signature of the spin liquid phase.
Can I ask a question?
Okay, please.
The peak of specific heat, low temperature in the order phase is just the phase transition to
It's a good question. So it's a really difficult point because if you calculate heat capacity at the Kitaev limit, still we have this kind of peak structure. So there is no clear connection between this low temperature peak and the ordered state. However, if we go inside this phase, then this low temperature peak signaling the development of the long-range spin-spin correlation, it's also found in our simulation. Then, in this sense, this peak signaling the development of the long-range spin-spin correlation in this side of the phase. And this phase, this temperature is a crossover temperature from the uncorrelated spins into the paramagnet, cooperative paramagnetic states. Please.
So, how large is the side effect? Is you dealing with this?
Okay, so
and also, did you check some?
yeah, final size. Here we have 32 sites, and this dotted one is a 24 site clusters.
And how low is the temperature? Like more than what?
Sorry, I missed it.
It's like high enough the temperature.
Yeah, this temperature, for example, high enough, and it's already converged. And around 10 Kelvin, the difference is not so large.
How is it divided by J?
J, okay, so this is 300 Kelvin. Largest temperature scale is 300 Kelvin.
And how? 300, and then it's like low.
This is a 0.3, and this is just 0.03.
0.02.
Yeah.
I suppose it's a bit too low.
No, but still, we have small finite size effect, even that.
You mean that your size effect is small enough if you check the sum rules, you need that kind of peak.
Sorry, some rules?
You need, you check the sum rule, right?
Yeah. And
But you can just check the peaks, or you can just suppress the peaks by keeping the sum rules in, so that you cannot exclude the fact that there might be that larger sum effect. 30 is, I think, not enough usually.
okay. Okay, yeah, please discuss that. Yeah.
I think if the temperature is lower than 0.1 J,
Yeah.
usually things will become.
Yes, yeah, of course. But yeah, the point here is that if I sum, as you already said, if I summing up them, then already this weight, how to say, degrees of freedom already exhaust almost all the degrees of freedom. So we don't care so much around the ultra low temperature scale because there is no another feature in addition to this temperature. Okay, sorry. Right. Okay, thank you very much for the question. And then we try to calculate the finite temperature excitation spectrum because as already said, the heat capacity has a difficulty in the experiment, but spin dynamics measure observed in the resonant X-ray scattering or neutron scattering is much more cleaner. Of course, there is many difficulty in the experiment, but anyway, it's much easier to access than easier than the
sorry,
heat capacity.
Could you go back to the previous slide?
Okay.
In your calculation, the transition between spin state and to the phase. In your calculation, is the transition between the two phases of first order or second order?
Sorry, this is just a finite size calculation. So far, we found this as a continuous phase transition.
Okay.
And if you calculate other techniques like IPEPs, I have no idea. Maybe it can be a first order, but it's still
Okay.
Then let's move on to the spectrum. And let me remind you why I'm interested at the finite temperature. Of course, the experiment done at the finite temperature. This is most important reason. But we want to find some finite temperature signature of the quantum spin decade instead of the alibi of the spontaneous symmetric breaking. But in addition to that, if you look at finite temperature, we can have a bonus in addition to that because the finite size, even if you calculate the finite size cluster, the finite temperature gives us a well-controlled behavior. thanks to the nearsightedness of the correlated system. Because at the finite temperature, correlation lengths become shorter than the final ground state. And it's already discussed by Walter Kohn for many years. His motivation is about nearsightedness in the ab initio calculation. For example, for if you calculate the semiconductors, then usually the electrons behavior determined from the really local nature of the crystals. This is the origin. But if you look at the frustrated magnetism, still the correlation lengths become really short at the finite temperature. So thanks to this nearsightedness, the finite temperature effect become really, size effect become not so severe. For example, let me remind you the heat capacity data from the sodium unit Bayesian Hamiltonian. And for example, above the or more or less 30 Kelvin, it's 1/10 of the dominant coupling. The size effect is nothing. Even if you go below, still the finite size effect is quite small. So in this sense, the frustrated magnets, the finite size effect at the final temperature become really small. Not so small, maybe you want to say, but anyway, we can control the finite size effect at the final temperature.
It's not always for the frustrating magnet. For example, in Kagome and in triangles, it's quite large.
In this sense, in the Kagome system, the remaining entropy at the low temperature is quite small. This is the reason why.
I don't agree with that because recently people have recognized that the specific heat is going to show again.
I mean that if you measuring the temperature dependence of the entropy, the remaining scale, the remaining entropy, amount of entropy is not so large in the Kagome.
We have also checked it.
Yeah, I know.
It's not really the case.
Yeah, I know. Because in this case, it's more or less half of the entropy
Yeah,
remains.
just mentioned that maybe this is a special case, but it's not always holding in frustrating magnetism.
Okay, so maybe we should discuss about in the much more quantitative fashion because
Yeah, but if we talk about temperature higher than 0.1, it's going to be fine. Almost all the sizes will last in the same curve.
yeah, because
if you go down below 1 place, 0.1 Kelvin, 0.1 J, not Kelvin. I think it's going to be.
Yeah, because in the Kagome lattice cases, the heat capacity has more or less the single peak and shoulder, and the peak temperature is more or less problem.
Oh, it's true, but if you do it with the 30 something, it's a bit different. So
Yeah,
it's
I know, but the remaining low temperature entropy is not so large.
well, compared to triangles, it's still large.
Yeah, compared to triangle, but
And it's
the
still,
point here is that we have a large entropy remaining around this temperature, more than half in this system. This is really important.
but for the Kagome lab is the 0.0 temperature entropy is like almost half, 4 plus more.
So I
Could you speak
don't
up,
agree.
please?
I don't agree. I don't agree.
Could you speak up, please?
I'm sorry. It's a mistake, but at least for the Kagome lab, below temperature 0.1, there still is a very large entropy.
But my point is that please compare with the peak temperature of the heat capacity. Just scale compare with the coupling is not so important. Because if you change the lattice structure and if you change the system, then it's not so useful. Please compare with the temperature dependence of the entropy. And the figure out, we should have some independent, temperature scale relevant to each systems. Here, the relevant temperature scale is this 2, and compare with 2 temperature, we should discussing about the behavior. So in this sense, that if we compare with the Kagome lattice, then we should pin down the temperature scale in the Kagome lattice. And in this sense, the 0.1 J here around here, but here is still we have a peak structure below this, and we keep the large entropy. But the problem is that in the Kagome lattice, the heat capacity peak is appear in this which temperature. And this is a really important point.
Yeah, it's a bit more higher. But,
Okay.
I think we need to discuss later on, but
Yeah, yeah.
not to be able to move.
Then and then my motivation. Okay. But anyway, yeah, we just stick to the higher temperature scale later. Okay, then another motivation coming from the experiment, because the experimental data for example, the ruthenium chloride, people believe that this compound is close to the Kitaev limit. I don't agree with this, but anyway, many people believe in. And then the temperature dependence is really large. If, for example, this is above the nail temperature of this system, and this spectrum is coming from the lower temperature, below the nail temperature. The horizontal axis is the momentum, and vertical axis is energy. The spectrum change a lot depending on the temperature. This is another motivation to calculate the finite temperature spectrum. So maybe I need to speed up. So to calculate many systems, we try to develop the convenient algorithm for the finite temperature spectrum based on the several already known mathematical tools. The finite temperature spectrum is in general calculated by using this Green's function. And here we have Boltzmann weight, and here we have eigenvalue, eigenvector, and eigenvalues of our Hamiltonians. And usually, if you want to calculate these guys, and maybe you can erase this closure, and you can have some operator forms inside here. And then if you naively calculate the complexity or computational cost and memory cost for this calculation, then it's scaled by the cubic of the Hilbert space size, and this is for the computational cost, and then this is for the memory cost. Usually, the complexity and the memory cost can reduce by using the sparseness of the Hamiltonian, but this is maximum cost. And of course, this kind of cost you don't need to pay. For a long time, there's many papers written by more or less independently by many authors about finite temperature spectrum. It started around 2003 by Dr. Itaka-san in the weekend. And if you calculate the real-time evolution of the finite temperature wave function, then you can obtain the spectrum by using the Fourier transformation. It's already studied by Dr. And however, this kind of the algorithm is a sequential, and it cannot be parallelized along the time axis. Maybe it could be a problem sometimes if you want to utilize the power of supercomputer. And another approach is the spectrum by the microcanonical ensemble, not the canonical ensemble, but microcanonical ensemble. If you if you construct some eigenvalues with some finite energy, it's excited state, then you can calculate some finite temperature spectrum by using the microcanonical ensemble. However, you need to determine the temperature independently for this kind of approach. So I'd like to make a much more convenient one to calculate the finite temperature spectrum with a supercomputer. So we try to re-examine our system. Sorry, I made a mistake here. Sorry, I should -1/2 here. Sorry. And to obtain this, we can start from the random vectors. And if you multiply the e to the -12 beta h Hamiltonian to the random vector, then you can obtain the finite temperature typical state. It can describe the finite temperature state. And by using this state, starting from the random vector, if you normalize this, then this vector is mimicked by this kind of formula. Here we have some square root of the partition function and the square root of the Boltzmann weight together with some complex phase. And here this is n is the eigenstate of the Hamiltonian. And if you can construct a spectral projector defined like this, then you can easily calculate the Green's function by using this typical pure state. However, the construction of this projector is not so easy, because if you can construct this, then you can obtain every information of your Hamiltonian. So let me approximate this spectral projection by using the contour integral of the Hamiltonian matrices defined like this. And if you apply this kind of a projector to some wave function expanded by the eigenstate, then this projector can filter in the eigenstate inside this range of the eigenvalues, like this. So this is really famous filter techniques used by the Professor Sakurai and Professor Sugiura, and it's called as Sakurai-Sugiura method in the applied mathematics. And usually in the applied mathematics, we just discretize this summation with the Riemann sum like this, and changing the theta by using some discrete angular degrees of freedom. And we can discretize this with some discrete point in the complex plane. And if you take a summation, then we can realize this projection. And usually this projection costs much, so people don't want to use this kind of approach. However, here we have some special structure, because here the important operator, Hamiltonian operator, is more or less the same with the different complex number appearing here. It's proportional to the identity matrix. And this kind of the inversion of the complex number minus h can be treated by the shifted Kirchhoff subspace method. And here we can utilize the shifted by CG method. CG is nothing but a conjugate gradient method. And the by CG method is applicable to this kind of complex number with Hermitian matrix. And this method found by Professor Frommer in the 2003, and it's extended by the Japanese people also. And here we already have a library to calculate this kind, to utilize this kind of Kirchhoff subspace method. It's implemented in the library K omega, developed by Dr. Kawamura in this institute. So I can utilize this method. Then if you're covering your energy axis, introducing this quantile integral like this, then you can end up with the Green's function by using this kind of spectral projection. And if you take a large discrete point limit together with the small radius limit, here epsilon is the radius of this circle and m is the number of the discrete point on this quanta, then you can obtain the exact Green's function. And as a byproduct, if you just take an inner product of this projected wave function, then you can obtain the probability distribution as a function of the energy, discretized energy. Then this kind of the probability distribution is also used in the nuclear physics by these authors, including the Professor Sakurai. He developed the Sakurai-Sugiura method. And this is some typical example of the density of state. Here I used a method to the 24-site cluster of the Kitaev model and obtain the histogram of the density of state. Horizontal axis is the energy, and the vertical axis is a histogram of the how many states appear in some small discretized energy range. And this is more or less looks like a Gaussian distribution. And actually speaking, this width is corresponding, it's related to the heat capacity, high temperature limit of the heat capacity. And if you measuring by using this kind of techniques, we have a really good news, because this finite temperature method, the error in this finite temperature method is scaled by the exponential of the minus entropy, roughly speaking. And if you measuring some expectation value for the operators with some typical state at the inverse temperature beta, then depending on the random state, initial random state, your observed quantity have a probability distribution like this, and the width is given by the standard deviation. And this standard deviation is scaled by this exponential minus entropy. And if you enlarging the size of the spin clusters from the 18 side to the 24 side, then this quantity becomes smaller and smaller. And for the high temperature, it's really small, and the low temperature it becomes larger. And this gives you this standard deviation. So if your system size is enough large, then this standard deviation becomes really small. And this is discussed by these papers. And even for the finite temperature spectrum, this situation also true. And actually, let me introduce some benchmark result for the 18 site antiferromagnetic Kitaev-Heisenberg. Here, it's more or less invisible, but here the solid line is the exact diagonalization result with the finite width with 0.01. And then this red belt or red area representing the standard width of the 1 sigma in the standard deviation. So in this sense, our algorithm is more or less exactly reproduce the exact result for the canonical ensemble, just reproducing the really detailed finite size structure. Then let me apply this method to the finite temperature signature to figure out the finite temperature signature of the proximity to the Kitaev spin liquid. Okay, so let me start with the global phase diagram for the Kitaev-Heisenberg. Here, the Kitaev coupling and the Heisenberg coupling is parameterized by phi like this for the 3 different bonds. And this is a phase diagram that we try to focus around here, starting from the 90°, and if you are enlarging this degree, phi, then we can go into the zigzag order phase at the ground state. Let me introduce some results from the Professor Christian Battista's group. And if we look at the classical spin dynamics in this region, starting from the Kitaev limit, and if you introduce the 10% of the Heisenberg coupling to this Kitaev limit, then you will reproduce the spin wave-like behavior. This green curve representing the spin wave structure, and this red part is a high intensity part of the SQ omega. Then if you entering from the Kitaev limit to some ordered state, then you will find the damped magnons below the Néel temperature even in the classical phases. Please remind this situation. Then if we go to the quantum limit, what will happen, I will show you. And starting from this phase diagram, with the 24-side cluster of the Kitaev-Heisenberg model, then if you changing the phi from 90 degrees to the 100 degrees, then we can covering the Kitaev spin liquid phase with the zigzag ordered phases. And this temperature scale is just coming from the temperature scale of the peak structure, 2 peak structure in the heat capacity. This is a high temperature peak temperature, and this is low temperature peak temperature. Okay. Then if we look at the spectral function higher than this high temperature scale, it's more or less the same. For this column, I show you the result for the Kitaev model, and this column result for the 100 degrees. So it's inside the zigzag order. There is more or less no difference. But if you lowering temperature lower than the high temperature peak, it's enough high in the experiment. But still already we have some difference at the really high energy. From the Kitaev limit to this Kitaev-Heisenberg system with the zigzag ordered ground state, we just introducing the less than 10% of the Heisenberg term if we compare in comparison with the Kitaev coupling. But still we have a difference, because please be careful, because here the temperature is at 0.2. It's larger than the Heisenberg coupling. And in addition to that, here I show you the spectrum from the omega 0.05 to the omega 1.05. So that this energy scale is enough higher than the additional Heisenberg coupling. But still we have some difference between the Kitaev limit and the Heisenberg limit. And if you lowering temperature, it's larger than the low temperature scale, but already we have some signature of the magnetically ordered phase in this lower low data, because here this bright spot is corresponding to the zigzag order observed, should be observed in the zigzag magnetically ordered phases. Then let me compare in the much more quantitative fashion. This is a classical result from the Kitaev limit and with the 10% of the Heisenberg coupling. Then if we compare with this data, we just picking up the spectrum at the gamma point, just cutting along this direction. And I have this kind of spectrum with a function of the omega. Here the red one is at the 100 degree, and the blue one is 90 degrees at the Kitaev limit. Its difference is not so visible, but if you measuring the the ratio between the peak energy scale and this width, then we will find a really striking difference. Here I used this kind of fitting curve to to extract the width and the temperature, the peak energy. Then if you take a ratio of the peak width gamma over the peak energy epsilon, then we can make this kind of color plot on top of the two energy scale the temperature phase diagram of this system. Then if you're starting from the high temperature, then this ratio is more or less half above this high temperature peak. This is corresponding to the uncorrelated spin behaviors. But if you lowering temperature below this temperature scale, then this ratio becomes smaller and smaller. And for the enough high temperature region, above the quantum spin liquid phases, this just reached to the just stopped above the 0.3. And if you checking the temperature dependence, that this ratio cannot be smaller above this quantum spin liquid phases, because we have some continuum spin excitation in the spin liquid phases. However, if you go into this zigzag ordered phases, then this ratio can be smaller than 0.3. And then as a typical example from the experiment, usually the square lattice Heisenberg model case is typically at the finite temperature, this scale is 0.1. So in this sense, if you lowering the temperature and if this number become 0.2 below the 0.3 and can be more or less below the 0.2, then it can describe the damped magnon phase with the magnetically ordered ground states. So in this sense, if you're measuring the peak width together, ratio between the peak width and the peak energy scale, then this gives you the finite temperature signature of the spin liquid phase, and it maybe give you some distance, quantitative distance from spin liquid phase in your real compound. Okay, let me summarize. Goal of my talk is how to characterize the quantum spin liquid at the finite temperature properties, and we propose a new algorithm for the finite temperature spectrum, and in combination with the shifted Fourier subspace method by CG method and the typical pure state. And we call this algorithm as a finite temperature Fourier subspace method for the spectrum, in short, FTK omega. And we found that the finite temperature signature of the Kitaev spin liquid phase really appear in the peak width of the spin excitation spectrum. And this ratio gives us a crossover behavior from the continuum excitation spectra to the damped magnon spectrum. And maybe it gives us a possible way to characterize how distant your materials from the Kitaev spin liquid limit. Okay, thank you very much for your kind attention.
So how does the surface curve of the point 3 look like in this space diagram?
Sorry, how?
The point 3 curve look like? Continue.
Below this temperature.
That is very important for you.
Right. And actually speaking, I already checked because Nassan, Professor Nasu already checked the Kitaev limit behavior. Sorry, not Nassan, but Yoshitake-san in the Professor Motome's group already checked the finite temperature behavior at this limit, and there is already confirmed by this ratio cannot be smaller than 0.3 at this range. So, but however, away from this and below this temperature scale, we have no reliable method for so far. So I just stop here because this temperature scale is quite safe. And from we can get rid of the finite size effect above this temperature.
But however, the criterion which value is the proper value for crossover, the 0.3 is the why 0.3?
Because
find the point 29.
It's not so quantitative. But for example, if you look at the curve here, then around this temperature, this ratio have a more or less the saturated behavior like this. Sorry, I also have data, but For example, in the Kitaev limit, this ratio looks like this, 0.3, and at the transition point, it looks like this, and above the transition point, its behavior look like this. Sorry, thank you very much. 0.2.
Well, maybe the related question is in order to quantify or characterize crossover, there are a lot of quantities, not only this one.
Yeah,
so this is the best quantity?
First of all, the way I calculate this is it's already observable in the experiment. But of course, we can have a much more different choices. For example, this method.
But for example, why you have chosen the K point at the gamma?
Okay. So for this system, it's a it is really convenient because from the classical analysis, we know that we have broad peak structure at the gamma point, and from the analysis, from the classical analysis, we know that this broad peak should be crossover to the magnum dispersion. So I choose this part because in the Kitaev limit we have a continuum here, but in the magnetically ordered phases, this should be going to the magnum dispersion. So I choose this point.
But even magnetically ordered states it's located at high energies, so magnum should dump.
Right. So this is the reason why I mentioned some typical scale in the finite temperature spectrum in the experiment. It's like a 0.1. And so far, the neutron scattering, maybe resolution of the neutron scattering or finite temperature broadening, the square lattice Heisenberg model is just around 0.1 in this width. So we can compare with this scale. So this is the reason why I choose that. Even in the finite temperature, the experiment gives us some limit, 0.1 or something. So if our curve is just go below this scale or just pointing along this scale, then we can judge that you will have a well-characterized magnum dispersion, dumped that magnum dispersion at the finite temperature. This is the reason why I call this behavior as a dumped magnum.
So in your talk, you mentioned that the other compounds, alpha, nucleophile, may not be the realization of Kitaev model, right? Can your kind of criteria use also in case?
Okay, so first of all, why I doubt is if you calculate the spin Hamiltonian from the first principle property, first principle way, then there is many group or many results, but always we found that there is a dominant Kitaev coupling and together with the gamma coupling, it's comparable with the Kitaev coupling. So this is the reason why I don't believe the Ruthenium chloride is located nearby the Kitaev limit.
Okay, but if you have you ever tried this kind of analysis based on the published data for this compound?
Actually, frankly speaking, not yet, because at least at the ground state spectral function, we have many trouble with the ab initio Hamiltonian. We cannot reproduce the spin gap at the M point in the Brilliant zone. This is corresponding to the zigzag order. And usually, this Kitaev gamma coupling has a Kitaev gamma. If we have Kitaev coupling and gamma coupling together with it, then we have some spin gap behavior, or we have strong anisotropy along the in-plane and the out-of-plane. It's kind of XY-like. So that we can have a spin gap at the endpoint. But this gap size is quite different in the ab initio model with and the experiment. If you calculate the ab initio spin excitation spectrum by using the linear spin wave, it's okay. It's comparable with the experiment. But if you do the exact method, like ED, calculating the spectral function, then the gap size becomes much smaller, and we cannot compare with the experimental data. So there is some additional factor in the real compound, ruthenium chloride. And together with this, quite different from the sodium iridate. If you compare with the heat capacity, temperature dependence of the heat capacity from the ab initio Hamiltonian for the ruthenium chloride, the experimental result doesn't match with the ab initio result. Temperature scale is quite different.
Quite different.
Even if you look at the high temperature peak. And there is no separation in the entropy. There's no half Plateau in the entropy. We shouldn't have, but anyway, there is a big difference.
So that is true for all the ab initio Hamiltonians that have been proposed so far?
Sorry, true.
So that statement is what is true for all the ab initio Hamiltonians that have been proposed for ruthenium trichloride?
Yeah.
So none of the models can reproduce the correct energy state of the peak?
Cannot, so far cannot.
I see.
Yeah. Of course, if you're tuning a little bit, then for example, the high temperature scale for the SQ omega or heat capacity data can be fitted. But if you look at, for example, the gap size in the SQ omega, then you need to introduce a quite large Kitaev coupling. For example, Takahumi-san already studied about this point. And so far, no ab initio model can describe everything observed in the experiment. Maybe for the sodium iridate, we should have a discrepancy in the ab initio Hamiltonian and the spectrum, but unfortunately for the sodium iridate, we cannot have a good quality data for the SQ omega. So now we should compare for the ruthenium chloride. So yeah, in this sense, I just prepared some tools to characterize the theoretical Hamiltonian to compare with the experimental data. So the actual research is just on the way.
I have a question about this phase diagram. I expect the fluctuations to be small in order of place. So is your
You mean, sorry, what kind of fluctuation?
so you have the quantum cases in there. I'm wondering if you can compare your result with the classical simulations. Did you find some difference?
Right. First of all, the peak width is much broader in the quantum cases. So in this sense, the quantum case is much. But let me be really careful, because the temperature scale in the quantum limit and the classical limit is a bit different. So that we should pin down which kind we should compare the temperature with some specific temperature scale in the quantum cases and the classical cases. And unfortunately, nearby the Kitaev spin liquid case, the temperature scale in the quantum and the classical is quite different. So in this sense, frankly speaking, we should be careful about the comparison, because here I just compare with for example, this data from the Christian's group is observed more or less around the ground state. It's really low temperature. And even if this low temperature scale, there is some finite width here and finite width here, and then we just compare with this. And so in this sense, that we should be careful. We should compare with the zero temperature limit or below this temperature scale, and we should calculate how much the magnum is dumped, because this is a finite energy magnum branch, so that we should have dumping even at the current temperature. But so far, we cannot reach to this temperature.
So in the Kitaev case, of course there is a difference between the classical and the quantum. There is a gap in quantum cases. But is there any difference?
Quantitatively different. But in qualitatively speaking, if you qualitatively speaking, there is a finite size with finite width, even in the classical case and both in the classical case and the quantum case. So in this sense, that this is more or less the same.
Yes, so is it possible for you to add a magnetic field, for instance, along the one direction? And
Of course.
see how it is?
Of course.
Repeat the same calculation?
Yeah, it's quite easy. Yeah. But frankly speaking, this result is first I derived this result for checking the applicability of my techniques. So that I didn't examine the magnetic field dependence node.
Thank you again.
Thank you very much.